Have you ever looked up at the stars and felt the weight of a question you couldn't quite put into words? Something deeper than what's out there, more primal than curiosity, more human than science. Something like, why is there anything at all? Not just stars and galaxies, not just planets or atoms, but everything: time, space, light, darkness, even thought itself. Where did it all come from? Did it have a beginning? Or has it always existed? For as long as humans have existed, we've asked these questions. At first, around fires, then under domed skies, now with telescopes that see across billions of light years, and yet, the mystery remains. In ancient times, we answered with stories. Creation myths filled with gods and chaos, with eggs cracking open into worlds, with cosmic trees whose branches held the stars. They were beautiful, they were symbolic, they gave us comfort and meaning. But eventually, we looked deeper, not because the myths failed, but because the universe whispered something more. We began to notice patterns. That the stars moved with precision, that light followed rules, that nature, beneath all its chaos, had structure. And from that structure, we began to extract knowledge, not just what things are, but how they became. That journey took centuries, from Aristotle to Newton, from Galileo's telescope to Hubble's deep field. Each step brought us closer to a shocking idea: that the universe had a beginning. A real one, not just in story, but in fact. Imagine everything, every atom, every galaxy, every ray of light, compressed into a single point, a point with no volume, no space around it, no time before it. Then, in an instant, expansion. Not an explosion in space, but the expansion of space. The birth of the cosmos, of dimensions, of time itself. We call it the Big Bang, but the name is misleading. It wasn't loud, there was no sound, because there was no air, no fireball, because there was no space for fire. The Big Bang wasn't a bang, it was the moment being emerged from non-being, where laws, constants, and particles blinked into existence. And from that came everything. In this documentary, we're going to dive into that mystery, not just how the universe began, but what it means for something to begin at all. We'll trace the history of human thought, from creation myths to quantum fields, from medieval scholars to modern satellites, from intuition to math. We'll explore why space is expanding, why the further we look, the younger the universe appears, why cosmic background radiation is like a fossil of light, and how inflation theory changed everything. We'll hear from Einstein, who bent time and space into a single fabric, from Georges Lemaître, a priest and physicist who first imagined a primeval atom, from Stephen Hawking, who asked, what if time itself had a beginning? And we'll explore the role of quantum mechanics, the strange world where particles flicker in and out of existence, and even nothing is unstable. But we won't stop there. We'll ask the uncomfortable questions. What came before the Big Bang? Was there a before? Could time have looped? Could our universe be just one of many? A bubble in an infinite foam? And what if the Big Bang wasn't the beginning, but a transition, a rebirth from a dying universe, a bounce from collapse into expansion? This isn't just science, it's philosophy. It's poetry written in equations. It's humanity's greatest detective story, told across billions of years. Because in searching for a beginning, we learn something about ourselves, that we are a species driven to understand, to find order in chaos, meaning in vastness, and unity in the unthinkable. So, if you've ever wondered, why is there something instead of nothing? Why is the universe the way it is, and not some other way? Why you exist at all, in this time, this place? Then stay with us, because we're about to travel to the edge of time, to the first flicker of light, to the very beginning. This is the story of how everything began, from the smallest particle to the farthest galaxy, from nothing to everything, born in darkness. Why myths were created long before telescopes, equations, or scientific theories, humanity looked up at the stars and asked a simple question: where did we come from? This question wasn't just about curiosity, it was about survival, meaning, and identity. Ancient people didn't have physics or astronomy. They had observation, imagination, and deep wonder, and to explain the world around them, they created myths. These cosmogonic myths, stories of how the universe began, were not random. They were carefully shaped by the environment, culture, and beliefs of each civilization. Myths explained the origin of light and darkness, order and chaos, time and matter. They gave people purpose, structure, and the illusion of control in a mysterious and often terrifying world. Mesopotamia. Creation through conflictone of the oldest known creation myths comes from Mesopotamia. In the Babylonian text Enuma Elish, the universe begins not with peace, but with violence, a cosmic war. In the beginning, there was only a vast, chaotic ocean, embodied by two deities, Apsu freshwater and Tiamat salt water. From their union, younger gods were born. But the noise and energy of these younger gods disturbed Apsu, who decided to destroy them. Tiamat resisted, but eventually chaos erupted. The god Marduk defeated Tiamat in battle and split her body in two. One half became the sky, the other, the earth. Here, creation is not a peaceful unfolding. It is a battlefield. Order emerges from conflict. The message is clear. The world is harsh, and survival requires strength. Egypt. Order from stillness. In contrast, the Egyptian cosmogony is more serene. The world begins as a still, dark, formless ocean called Nun. From it rises a single mound, the Benben, and atop it stands the first god, Adam. Through sheer will, Adam creates other gods who shape the sky, the earth, air, and all forms of life. Egyptian creation is centered around Maat, the principle of balance and order. Chaos is not fought with weapons, but with ritual, harmony, and cosmic justice. Pharaohs were believed to maintain this order on earth, acting as intermediaries between gods and men. The Egyptian view suggests a cosmos that is fragile, but noble, not born from war, but from awakening. India cycles without beginning. In Vedic and Hindu traditions, the idea of a single beginning is irrelevant. Time is not linear. The universe doesn't start, it cycles. Creation, destruction, and rebirth are eternal. The Rig Veda, one of the oldest texts in the world, presents ambiguous and poetic views of creation. One famous hymn, the Nasadiya Sukta, questions whether even the gods know how the universe began. It suggests that perhaps the origin is unknowable. Later Hindu cosmology introduces gods like Brahma creator, Vishnu preserver, and Shiva destroyer. But even they operate within an eternal cycle of yugas, vast cosmic ages. This worldview embraces uncertainty. Instead of demanding an answer to how did it all begin, it asks, does beginning even make sense? China, the cosmic egg, and the ancient Chinese cosmogony also mixes philosophy with myth. In one version, the universe begins as a cosmic egg, a symbol of potential. Inside it, chaos and order are mixed. Eventually, the giant Pangu awakens and breaks the egg. He separates yin from yang, creating the earth and the sky. Pangu stands between them, holding them apart. When he dies, his body becomes the mountains, rivers, and stars. Other myths emphasize the role of Che, the vital force that animates all things. Creation is not a one-time event, but a constant unfolding of energy in balance. Greece. From chaos to cosmos, ancient Greeks were among the first to transform myth into something approaching philosophy. In Theogony by Hesiod, the universe begins with chaos, not disorder, but a yawning emptiness. From chaos came Gaia Earth, Tartarus the underworld, and Eros desire. These primordial entities gave rise to titans, gods, and eventually humanity. Conflict is central, but the myth moves toward increasing structure, toward cosmos, the Greek word for order. Later Greek thinkers, like Anaximander and Heraclitus, began to interpret these myths metaphorically. They searched for underlying principles, like appear on the boundless or logos reason, to explain the universe. Patterns across cultures. Despite the differences, many creation myths share striking similarities. Primordial waters, found in Mesopotamia, Egypt, and others. The ocean as origin. Cosmic egg, seen in Hindu, Chinese, and even Finnish traditions. Separation of sky and earth. Pangu holds them apart. Adam creates them. Marduk divides them. Creation from body. Tiamat becomes sky and earth. Pangu's body becomes the world. These shared symbols suggest that human imagination, across time and culture, tries to grasp the unknown with familiar metaphors. Water, body, breath, birth, light. Were **** from myth to philosophy. The first shift toward science as civilizations evolved. Myths gradually gave way to more abstract thought. The line between myth and early science blurred. Philosophers like Thales proposed that everything came from water, not a god of water, but water itself. Anaximenes chose air. Pythagoras saw numbers as the building blocks of reality. These weren't scientific theories as we know them today, but they were radical. They replaced gods with principles, myth with observation. It was the first step toward the scientific worldview, a new kind of cosmogony, one based not on faith, but on reason. Why these myths still matter today. We have the Big Bang, quantum fields, string theory, but the urge to tell a story about the beginning, to ask what came before us, has never gone away. Ancient myths may not be factually true, but they speak to emotional truths. They connect us to ancestors who looked up at the same stars and wondered the same things. These myths are not wrong. They are poetic blueprints of curiosity. And before there was science, there was story. Every equation we write today is part of the same ancient journey, the search for origin, meaning, and place. For most of human history, the night sky was a mystery filled with gods, spirits, and omens. People told stories about the stars, myths that explained their origins, motions, and meaning. The heavens were seen not as a system of objects obeying natural laws, but as the realm of divine will. Thunder was the anger of the gods, eclipses were warnings. Comets were harbingers of doom, but something changed. Thousands of years ago, a new kind of thinking began to emerge, one that asked not just what, but why. In ancient Mesopotamia and Egypt, early civilizations began to record astronomical events. They tracked the movements of the moon and sun to create calendars. Though often tied to religious practices, this was the beginning of observation, the seed of science. The real transformation began in ancient Greece. Around the 6th century BCE, thinkers like Thales of Miletus began to suggest that natural phenomena might have natural causes. He proposed that water was the fundamental substance of all things, not because of a divine vision, but through reasoning. His student, Anaximander, speculated that the earth floated in space and was not held by anything. These early ideas sound primitive now, but they represented a radical shift. The universe could be understood by logic and observation. Pythagoras, living in the 6th century BCE, believed the universe was built from numbers. He and his followers studied the mathematical relationships in music and geometry. They saw harmony not just in sound, but in the cosmos. This was one of the first attempts to unite mathematics and the physical world, a foundation that would shape science for millennia. Then came Plato and Aristotle. Plato believed in a perfect, eternal world of forms, and saw the heavens as reflecting this perfection. He encouraged the study of geometry as the language of the cosmos. His student Aristotle, though often criticized today, developed a system of physics that dominated Western thought for nearly 2,000 years. He argued that Earth was the center of the universe, that objects fall because they seek their natural place, and that the stars were fixed on crystalline spheres. Wrong. Yes, but powerful. Aristotle's system was appealing because it explained everything with purpose. Every object had a reason for its motion. It was a universe of order, not chaos, and one that could be reasoned through. Still, not all Greek thinkers agreed. Aristarchus of Samos, in the 3rd century BCE, proposed something revolutionary, that the Earth moved around the Sun. His heliocentric model came almost 1,800 years before Copernicus, but it was largely ignored. The idea was too radical for its time. While many Greek ideas faded with the fall of their city-states, one place kept their intellectual flame alive: Alexandria. In Egypt. Founded by Alexander the Great in the 4th century BCE, Alexandria became the most important center of knowledge in the ancient world. Its library, the Library of Alexandria, was legendary, housing hundreds of thousands of scrolls from across the known world. Here, scholars from different cultures met, debated, and built on each other's ideas. Among them was Eratosthenes, who in the 3rd century BCE made one of the most astonishing measurements in history: the circumference of the Earth, by comparing the angle of the sun's rays at 2 different cities during the summer solstice. He calculated Earth's size with remarkable accuracy, all without leaving Egypt. It was a triumph of geometry, logic, and observation. Another genius of the Alexandrian age was Hipparchus, who created the first star catalogue, discovered the precession of the equinoxes, and developed a system for predicting solar and lunar eclipses. His work laid the groundwork for later astronomical models, but perhaps the most influential of all was Claudius Ptolemy, who lived in the 2nd century CE. In his great work Almagest, Ptolemy presented a detailed geocentric model of the universe, a cosmos where the Earth sat unmoving at the center, and planets moved in complex orbits called epicycles. Though wrong, the model was elegant, predictive, and accepted for over 1,000 years. It became the standard in both the West and the Islamic world. When the Roman Empire collapsed, much of this ancient knowledge might have vanished, but it didn't. Instead, it was preserved and expanded during the Islamic Golden Age, which began in the 8th century. Across cities like Baghdad, Damascus, and Cordoba, scholars translated Greek texts into Arabic, commented on them, and pushed their ideas further. This period was not just about preservation, it was a period of innovation. Figures like Al-Biruni, Al-Hazan ibn al-Haytham, and Avros ibn Rushd laid the foundations for the scientific method. Al-Hazan, for instance, used experimentation to understand optics and vision, centuries before Western scientists adopted similar methods. He wrote about how we must doubt what we see, test it through observation, and refine our theories. This wasn't just philosophy, it was science in action. In astronomy, Al-Arkali, Al-Tusi, and Ulugh made refinements to planetary models, observed celestial motions, and challenged the Ptolemaic system. They invented new instruments and improved mathematical tools like trigonometry, all vital to the eventual overthrow of geocentrism. This Islamic science was then transmitted back to Europe through translations, especially in Spain and Sicily, and helped spark the European Renaissance. It was here, in the late Middle Ages, that the torch of scientific inquiry passed again, this time to the West. In 1543, a quiet Polish church canon published a book that would change the world. Nicolaus Copernicus's De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres. His idea: the Earth was not the center of the universe. Instead, the Sun stood at the center, and the Earth, like the other planets, revolved around it. This heliocentric model was radical. It challenged centuries of belief, religious doctrine, and the authority of Ptolemy's geocentric system, but Copernicus offered little proof. His model was mathematically elegant, but not vastly more accurate than the Ptolemaic one. Still, he cracked the door open. Others would push it wide. One of them was Johannes Kepler, a German mathematician who inherited the precise observational data of Tycho Brahe, one of the last great naked eye astronomers. Kepler used that data to uncover something extraordinary. Planets move in ellipses, not perfect circles, with the sun at one focus. This violated ancient assumptions of celestial perfection, but it matched the sky far better. Kepler's 3 laws of planetary motion gave real predictive power too. The heliocentric model. They weren't just ideas, they were measurable truths. Meanwhile, in Italy, Galileo Galilei turned a new invention, the telescope, toward the heavens. What he saw was shocking: craters and mountains on the moon, moons orbiting Jupiter, phases of Venus. These were direct blows to the geocentric view. If celestial bodies had imperfections, and not everything orbited the Earth, then the old model was crumbling. Galileo didn't stop at observation. He became a public advocate for the Copernican system, and clashed with powerful institutions. Because of it, his eventual trial and house arrest are legendary, but his legacy is deeper. He championed a way of thinking where observation and reason mattered more than tradition. At the same time, the tools of mathematics were growing stronger. Logarithms, decimal notation, and algebraic methods became widespread. The language of nature was no longer mysticism, it was numbers. These developments set the stage for a final transformation, a synthesis of all these threads into a coherent, universal system of nature. That task fell to a man who would define modern science itself, Isaac Newton. In 1687, Isaac Newton published Philosophiae Naturalis Principia Mathematica, perhaps the most influential scientific book ever written. With this one work, Newton unified heaven and earth, the motion of a falling apple, and the orbit of the moon, he claimed, were governed by the same force, gravity. He formalized this in his law of universal gravitation and 3 laws of motion, concepts that provided a mathematical framework to describe how everything moves. It was elegant, predictive, and testable. Suddenly, the universe looked knowable, calculable, and even inevitable. Newton's work was revolutionary not just for what it said, but for how it said it. He combined observation, mathematics, and experiment into a method that became the gold standard, the scientific method. His laws could predict the path of a cannonball or a comet. They let us chart the heavens with astonishing accuracy. Astronomy transformed from a speculative art into a quantitative science. Newton stood on the shoulders of Copernicus, Kepler, and Galileo, and in doing so, gave humanity its first coherent, mechanical universe. For the first time, we had a model that worked, that didn't rely on myths or authority, but on equations and evidence. The world, and the cosmos, became a machine, vast and elegant, driven by forces that could be understood. But even Newton knew his vision wasn't the final word. "I do not know what I may appear to the world," he wrote, "but to myself I seem to have been only like a boy playing on the seashore. Whilst the great ocean of truth lay all undiscovered before me. And that ocean, vast, deep, and dark, is what future scientists would begin to explore. From ancient myths to the mathematics of motion, this journey transformed our understanding of reality. The groundwork had been laid. The stage was now set for the 20th century's next revolution, one that would break Newton's machine and bend time and space itself. But it all began here, with the birth of science. When Newton wasn't enough at the dawn of the 20th century, science stood on what seemed like solid ground. Isaac Newton's laws had ruled physics for over 2 centuries. They described the motion of planets, falling apples, and even the tides. His universe was like a perfect machine. Space was absolute. Time ticked uniformly for all, and gravity was a force acting across invisible lines. But cracks had begun to form. In the late 1800s, experiments like Michelson and Morley's showed that light didn't behave the way Newtonian physics predicted. The speed of light appeared constant, no matter how fast the observer was moving. This contradicted classical expectations. If light was a wave moving through some invisible ether, why couldn't we detect our motion through it? Physicists were baffled. Some tried to patch Newton's laws with new assumptions. Others dismissed the data. But a young patent clerk in Switzerland, Albert Einstein, chose a different path. He questioned the very foundation of space and time, Einstein's first leap. Special relativity in 1905. Einstein published a paper that would forever change physics, on the electrodynamics of moving bodies. This was the birth of special relativity. Einstein proposed a simple postulates. The laws of physics are the same in all inertial frames, places moving at constant speeds. The speed of light is always the same, no matter how fast you're moving. From these, he derived something astonishing. Time and space are not absolute. They're flexible, relative, dependent on the motion of the observer. If you're moving fast, really fast, close to the speed of light, time slows down for you compared to someone at rest. This isn't science fiction. It's measurable. We've confirmed it with atomic clocks on fast-moving jets and satellites, even length contracts. A fast-moving spaceship appears shorter to an outside observer, and events that look simultaneous to you may appear to happen at different times to someone else. This concept, that time is not universal, was a profound shock to centuries of thought. Special relativity explained the odd behavior of light and much more. But it had a limitation. It only worked for objects moving at constant speeds. No acceleration, no gravity. Einstein wasn't satisfied. Gravity was still trapped in Newton's world. He wanted more. The principle of equivalence. Here came Einstein's second stroke of genius. He realized that there was a deep connection between acceleration and gravity. If you're inside a sealed elevator, you can't tell whether the force pushing you to the floor is from gravity or because the elevator is accelerating upward in space. This idea, the principle of equivalence, became the seed for a deeper theory. Einstein imagined light beams inside that elevator. If the elevator is accelerating upward, a beam of light entering one side will hit the opposite wall slightly lower, tracing a curved path. But wait, if acceleration is equivalent to gravity, then gravity must also bend light. This was revolutionary. Newton saw gravity as a force acting at a distance. Einstein was about to say something much stranger. Gravity, the warping of space and time itself. But to describe that, he needed new mathematics. Over the next 10 years, Einstein worked with curved geometry, drawing on the ideas of Riemann and Gauss, and in 1915, he completed what many call the most beautiful theory in physics. Gravity becomes geometry in 1915. Albert Einstein presented his greatest achievement, the general theory of relativity. Unlike Newton, who saw gravity, a force pulling objects toward one another, Einstein reimagined it as a consequence of how mass and energy curve space and time. His famous field equations describe how matter tells space-time how to bend, and curved space-time tells matter how to move. It was a breathtaking idea. Imagine a trampoline with a heavy bowling ball in the center. Now roll a marble around it. The marble's path curves, not because there's a mysterious pulling force, but because the surface it moves on is curved. Einstein's equations say the same thing is happening in the universe, except not in a two-dimensional trampoline, but in four-dimensional space-time. The sun curves the space-time around it, and Earth moves along that curvature. It's not being pulled. It's following the straightest path possible in a curved geometry, what we call a geodesic. Predictions and proof. Einstein's theory made bold predictions. It said that time itself would slow down in strong gravitational fields, something called gravitational time dilation. It said that light would bend when passing near massive objects, and it suggested that the universe might be dynamic, expanding or contracting, rather than static. At the time, most of these predictions sounded absurd. But just 4 years later, in 1919, during a solar eclipse, British astronomer Arthur Eddington photographed stars near the Sun and found they had shifted positions. The starlight had bent as it passed through the sun's gravity, just as Einstein predicted. The news made headlines around the world. Einstein became a scientific celebrity overnight. His equations also hinted at other strange phenomena. Black holes, places where spacetime becomes so curved that not even light can escape. These were predicted by Carl Schwarzschild shortly after Einstein published his equations. Though Einstein himself was skeptical they could exist, today, black holes are not only accepted, they're observed. From the orbits of stars at galactic centers to the groundbreaking image of a black hole's shadow taken in 2019, general relativity has passed every test. Ripples in spacetime, gravitational waves. Another consequence of Einstein's theory was the prediction of gravitational waves. Ripples in the fabric of spacetime caused by massive accelerating bodies, like to black holes orbiting each other. For a century, these waves remained hypothetical. They were too weak to detect. But in 2015, exactly 100 years after Einstein's publication, scientists at the LIGO Observatory made history. They detected gravitational waves from two merging black holes over 1 billion light-years away. It was a moment of triumph for Einstein's vision. We had not only confirmed his theory, but opened a new window to observe the cosmos, not with light, but with gravity itself. Relativity in everyday life. It's easy to think of Einstein's theories as abstract or irrelevant to daily life, but they shape our modern world more than we realize. Your smartphone's GPS depends on both special and general relativity. Satellites in orbit experience less gravity and move faster than we do on Earth. Without correcting for time dilation, your GPS would drift by several kilometers each day. Time, space, and gravity are fixed absolutes. They are dynamic, interwoven aspects of the same fabric. And thanks to Einstein, we now understand that the universe is not a static stage where events unfold. It's an active participant in the cosmic dance. The legacy of Einstein's revolution in Stein's theories reshaped not just our understanding of gravity, but the entire framework of physics. They paved the way for modern cosmology, the study of black holes, the Big Bang theory, and quantum field theory in curved space. Yet, for all their success, general relativity and quantum mechanics, the other great pillar of 20th century physics, remain fundamentally incompatible. Finding a theory that unifies them is one of science's greatest unsolved challenges. Still, Einstein's insights endure. His vision taught us to question the obvious, to imagine the impossible, and to see the universe not as a static clockwork, but as a living, dynamic continuum. In bending space and time, Einstein bent the arc of human knowledge forever. Asterisk, 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 asterisk. Georges Lemaître and the birth of the Big Bang in the early 20th century. Our understanding of the cosmos stood at a crossroads. Einstein had just redefined gravity as the curvature of space and time, and his equations allowed for a dynamic universe, one that could expand or contract. But like many of his peers, Einstein found the idea unsettling. He preferred a static, eternal universe, unchanging and infinite. To preserve this vision, he added a fudge factor to his equations, the cosmological constant, a term that counteracted gravity and held the universe in balance. But soon, a quiet revolution began, not in Berlin or London, but in Belgium, led by a man who wore both a priest's collar and a physicist's gaze. Georges Lemaître, the priest-physicist who dared to expand the universe in 1894. Georges Lemaître was a brilliant mind torn between two worlds, science and spirituality. After serving in World War I, he studied physics and theology, ultimately becoming a Catholic priest and an accomplished astrophysicist, but he was no dogmatist. Lemaître believed that science and faith addressed different questions, while theology concerned the purpose of the universe. Science dealt with its mechanics. In 1927, just 2 years after Edwin Hubble had begun making his astronomical observations at Mount Wilson, Lemaître published a paper that would quietly reshape cosmology. Using Einstein's general relativity, He showed that the universe should be expanding. His mathematics predicted it. More astonishingly, he tied this expansion to the observed redshifts of distant galaxies. Galaxies weren't just sitting in space. Space itself was stretching, carrying them away like raisins in a rising loaf of bread. Few noticed. The paper was published in an obscure Belgian journal, in French, and received little international attention. But Lemaitre's insight would soon prove prophetic. Redshift and the smoking gun at the time, astronomers were noticing something peculiar. The light from distant galaxies appeared redshifted, stretched toward longer, redder wavelengths. This was similar to the Doppler effect, where the pitch of a siren lowers as an ambulance moves away. If light behaved the same way, redshift could indicate that galaxies were receding from us. Edwin Hubble, working with Milton Humason, began collecting precise data on these redshifts. By 1929, Hubble published a groundbreaking result. The farther away a galaxy is, the faster it seems to move away. This relationship became known as Hubble's law. But what Hubble didn't offer was a theoretical explanation for why the universe was expanding. Lemaitre already had that answer. When Lemaitre learned of Hubble's results, he pointed out that he had predicted this expansion 2 years earlier, not just empirically, but mathematically. In 1931, his paper was translated into English and published in the journal Monthly Notices of the Royal Astronomical Society. The global scientific community finally took notice. The primeval atom, a radical proposal, went further. If the universe is expanding, then it must have been smaller in the past. Go back far enough, and you reach a time when all matter and energy were compressed into a single, ultra-dense point. Lemaitre called this the primeval atom, a cosmic egg that exploded, giving rise to space and time. This was a bold and controversial idea. The term exploded was not meant to suggest a bomb going off in space, but rather that space itself began expanding from a highly compact state. There was no outside to the explosion. The explosion was of space itself. Many scientists scoffed. British astrophysicist Fred Hoyle, a proponent of the steady-state theory, which claimed the universe had always existed and always would, mockingly referred to Lemaitre's idea as the Big Bang, a term meant as an insult. Ironically, the name stuck. Lemaitre, however, was undeterred. He argued that general relativity, combined with astronomical observations, strongly supported a beginning to space-time. This idea made some physicists uncomfortable, as it seemed to echo religious creation myths. But Lemaitre was careful to keep his theological views separate from his physics. He once told Pope Pius XII not to treat the Big Bang as scientific proof of divine creation. Science, he said, should not be used as a tool of religious validation. Einstein's change of heart. Even Albert Einstein was skeptical at first. In 1933, when Lemaitre presented his expanding universe model at a scientific conference in California, Einstein reportedly said, "Your calculations are correct, but your physics is abominable." But that changed. Later that year, Einstein and Lemaitre took a famous walk through the California Institute of Technology gardens. After hearing more about the model, Einstein admitted he had been wrong. "This is the most beautiful and satisfactory explanation of creation I have ever heard," he said. He even called his introduction of the cosmological constant the greatest blunder of my life, though historians debate whether he actually used those words. Regardless, Einstein accepted that the universe was expanding, and Lemaitre had been right all along. From theory to foundation through the 1940s and 1950s, Lemaitre's model gained more traction, especially as astronomers continued to observe redshifts and map the large-scale structure of the cosmos. Eventually, physicists like George Gamow, Ralph Alpher, and Robert Herman expanded on Lemaitre's ideas. They predicted that if the universe began in a hot, dense state, it should have left behind a faint glow, cosmic microwave background, radiation. This glow, a kind of afterglow from the early universe, would be cold now, but detectable. that prediction would come true in 1965, when Arnaud Penzias and Robert Wilson accidentally discovered the cosmic background radiation while working on a radio telescope in New Jersey. The signal was uniform in all directions, exactly as the Big Bang model predicted. From that point on, the Big Bang became the dominant cosmological model. Lemaitre's once dismissed theory had become the bedrock of modern cosmology. Legacy of Lemaitre. Lemaitre never won a Nobel Prize, though many believe he deserved one. In his lifetime, he witnessed the transformation of his controversial theory into mainstream science. He remained humble, never seeking the spotlight, always emphasizing the distinction between metaphysical questions and scientific ones. Today, we recognize Lemaitre not just as the father of the Big Bang, but as a pioneer who saw the universe as a dynamic, evolving entity. His work opened the door to modern cosmology, dark energy, cosmic inflation, and the ongoing quest to understand what came before time itself. His blend of faith and reason, of curiosity and humility, stands as a rare and inspiring example in the history of science. The Big Bang Theory began as a bold idea, a radical departure from the static universe imagined by earlier generations. But bold ideas in science require evidence. Without solid observational support, they remain speculation. So, what convinced scientists that the universe actually began in a hot, dense state and has been expanding ever since? In this chapter, we'll explore the three pillars of evidence that have cemented the Big Bang as the dominant cosmological model: the redshift of galaxies, the cosmic microwave background radiation, the abundance of light elements. Let's start with a discovery that took place in the 1920s, one that changed everything. 1. Galactic redshift and the expanding universe. In the early 20th century, most astronomers believed that the Milky Way was the entire universe, but as telescopes improved, astronomers like Edwin Hubble began noticing strange nebulae that didn't seem to belong to our galaxy. Were these distant galaxies? To answer this, astronomers analyzed the light coming from these objects, and what they found was surprising. Many of the light spectra showed a redshift, a shift toward longer wavelengths. This wasn't simply a matter of color. It meant these galaxies were moving away from us. And the farther away a galaxy was, the faster it appeared to recede. This observation led to a revolutionary conclusion: the universe is expanding. Imagine blowing up a balloon with tiny dots on its surface. As the balloon inflates, every dot moves away from every other dot. The universe is like that balloon, but in 3 dimensions. And if everything is expanding now, it must have once been much closer together. This was the observational proof that Georges Lemaitre's hypothesis of a primeval atom needed. It transformed the idea of a beginning from speculation into serious science. But redshift alone wasn't enough. Could there be deeper relics of the early universe? 2. The cosmic microwave background radiation, CMB. If the universe began in a hot, dense state, as the Big Bang suggests, then it must have been filled with light. At first, the universe was too hot for atoms to form. Electrons and protons existed in a plasma, constantly scattering photons. But after about 380,000 years, the universe cooled enough for neutral hydrogen atoms to form. This process, called recombination, allowed photons to travel freely for the first time. That ancient light is still around today. But over billions of years, the expansion of the universe stretched its wavelengths. What was once searing hot radiation is now cold, faint microwave energy, filling every part of the cosmos. This is the cosmic microwave background, or CMB, one of the most important discoveries in the history of science. It was accidentally detected in 1964 by Arnaud Penzias and Robert Wilson, who were working on a satellite antenna. They found a persistent noise, a faint hiss, that came from every direction in the sky. After ruling out all sources of interference, they realized they had discovered the afterglow of the Big Bang. The CMB is incredibly uniform, but not perfectly so. Tiny variations in its temperature, just a few millionths of a degree, show the early seeds of structure in the universe. These were the slight over and under densities that would eventually grow into galaxies, stars, and planets. Today, satellites like COBE, WMAP, and Planck have mapped the CMB with incredible precision. These observations give us a snapshot of the universe as it was just 380,000 years old. That's less than 0.003% of its current age. The CMB is not just a confirmation of the Big Bang. It's a treasure trove of data that tells us about the age, composition, and geometry of the universe. 3. The abundance of light elements. But there's even more. The Big Bang Theory doesn't just explain the large-scale structure of the universe. It also makes precise predictions about the chemical elements we see today. In the first few minutes after the Big Bang, a period known as Big Bang nucleosynthesis, the universe was hot and dense enough for nuclear reactions to occur. During this brief window, protons and neutrons fused to form the first atomic nuclei. The theory predicts specific ratios of light elements, such as about 75% hydrogen, around 25% helium, traces of deuterium, helium-3, and lithium-7. These aren't random numbers. They're based on well-understood nuclear physics. And when we look at the oldest stars and most pristine gas clouds, places relatively untouched by stellar processes, we find exactly these ratios. This is stunning confirmation. The predicted abundances match the observed ones across the universe. No other theory, not steady-state cosmology, not alternative models, explains this with such accuracy. This evidence was crucial in the 1970s and 1980s, when debates about the Big Bang were still active. The match between theory and observation gave scientists great confidence that the model was not just plausible, it was correct. Additional clues from modern cosmology. While the three pillars, redshift, CMB, and light elements, form the core, modern cosmology provides even more supporting evidence. Large-scale structure, the way galaxies cluster on vast cosmic scales, matches the patterns predicted by early fluctuations in the CMB. Gravitational lensing, light from distant galaxies is bent by the mass of closer objects, a phenomenon predicted by Einstein's relativity and used to test the distribution of matter in the early universe. Dark matter and dark energy, while not directly part of the original Big Bang theory, observations of galaxy motion and cosmic acceleration point to invisible forces that shape the evolution of the universe. These, too, are consistent with the model's framework. Is there a better explanation? You might wonder, could all this evidence still fit another theory? In science, the best models aren't just the ones that explain what we already know. They also predict things we didn't yet observe. The Big Bang Theory has done exactly that, from the existence of the CMB to the proportions of helium. Alternative models have been proposed, like the steady-state theory or cyclic universes, but none have matched the predictive power or observational consistency of the Big Bang. That doesn't mean we stop questioning. In fact, some of the biggest mysteries in cosmology today, like the nature of dark energy or what happened before the Big Bang, require thinking beyond the standard model. But those explorations begin from a well-supported foundation, and that foundation is the Big Bang. Recap: the power of evidence. Let's briefly review the three key pieces of evidence. Redshift of galaxies shows the universe is expanding. Cosmic microwave background, the cooled, stretched light from the early universe, a visible afterglow. Abundance of light elements matches nuclear predictions from the universe's first minutes. Together, they paint a consistent picture. The universe had a beginning. It began in an extremely hot, dense state, and has been expanding and cooling ever since. This may not tell us why it began, but it tells us how it unfolded. And that is a monumental achievement of human curiosity, mathematics, and observation. When we say the Big Bang, we usually mean the moment our universe began, a hot, dense state from which everything expanded. But what if we ask the question no one dared to ask in ancient times? What came before the Big Bang? At first glance, it seems like nonsense. The Big Bang wasn't just the birth of matter and energy, it was the beginning of space and time themselves. Asking what came before might be like asking what's north of the North Pole. But modern physics is full of surprises. In this chapter, we'll explore several possibilities, each more mind-bending than the last. One, the classical singularity, and its problems in the simplest versions of the Big Bang model. When we trace the universe backward, density and temperature rise without limit until we reach a point of infinite density and zero volume, a singularity. This singularity marks the beginning of time in classical general relativity. But infinities in physics are usually signs that the theory has broken down. In fact, general relativity can't describe what happens at or before the singularity. It simply runs out of tools. This is a huge problem. To go further, we need to bring quantum mechanics into the picture. After all, the early universe was tiny, smaller than an atom. At such scales, gravity and quantum physics must work together. But our current theories can't fully combine them. We don't yet have a complete quantum theory of gravity. Still, physicists have developed several frameworks that offer glimpses into what might have happened before the Big Bang. Let's explore some of them. 2. Cosmic inflation and the quantum seeds of the universe. A theory of cosmic inflation, developed in the 1980s by Alan Guth and others, proposes that in the earliest fractions of a second, the universe underwent an exponential expansion, much faster than the normal Big Bang expansion. This inflationary phase smoothed out the universe and planted the seeds for all the structures we see today, via quantum fluctuations that were stretched across vast cosmic scales. But inflation doesn't necessarily explain the singularity itself. In fact, it raises a new question. What triggered inflation? Some versions of inflation theory suggest that inflation is not a one-time event, but an eternal process, creating countless pocket universes in a larger multiverse. In such models, our Big Bang is just one bubble in an ever-inflating cosmic sea. This brings us to the next possibility. 3. The multiverse and eternal inflation. In eternal inflation, quantum fluctuations cause inflation to continue forever in some regions, while other regions drop out and form individual universes like ours. Each of these universes can have its own physical laws, constants, and properties, forming a vast multiverse of possibilities. In this view, the Big Bang was not the beginning of everything, just the beginning of our observable universe, but eternal inflation leads to deep philosophical and scientific questions. How can we test the existence of other universes? Do they interact with ours? Are there regions of the cosmos where time flows differently? Some physicists argue that eternal inflation pushes us beyond the realm of empirical science. Others see it as the logical consequence of known physics. Still, inflation doesn't fully remove the question of before. What came before inflation itself? 4. The quantum bounce. Loop quantum cosmology of the most fascinating alternatives comes from a theory known as loop quantum gravity (LQG), which attempts to quantize space itself. In loop quantum cosmology, a simplified model based on LQG, the universe doesn't emerge from a singularity. Instead, when density reaches a critical level, quantum gravity causes a bounce. Imagine the universe contracting, reaching a minimum size, and then bouncing back into expansion, a process known as the Big Bounce. In this scenario, the Big Bang was not the beginning of time, but a transition between a contracting universe and our current expanding phase. This idea eliminates the singularity, and some models even preserve information from the previous universe. Could echoes of a past cosmos be imprinted in our own? We don't yet have definitive evidence, but the possibility is thrilling. 5. String theory and the ekpyrotic universe. Another approach to quantum gravity comes from string theory, which proposes that the fundamental building blocks of reality are not particles, but tiny vibrating strings. Some versions of string theory suggest that our universe is a three-dimensional brain floating in a higher dimensional space. In the ekpyrotic model, proposed by Paul Steinhardt and Neil Turek, the Big Bang was caused by a collision between two such brains. Each collision creates a new universe, and the cycle repeats. This cosmology doesn't start with a singularity, but with a pre-existing spacetime that has its own dynamics. Like the bounce model, the ekpyrotic universe suggests that time extends infinitely into the past. We are just one iteration in a potentially endless sequence of cosmic events. Still, these models rely heavily on theoretical physics that is not yet testable, such as extra dimensions and brain dynamics. 6. The no-boundary proposal, time without a beginning. Some physicists have gone even further. In the 1980s, Stephen Hawking and James Hartle proposed the no-boundary hypothesis, based on quantum cosmology. In this view, the early universe is described not by classical time, but by imaginary time, where the concept of before loses its meaning. Think of time as a curve on a globe. Near the South Pole, directions become indistinct. There's no south of the South Pole. Similarly, at the beginning of the universe, time becomes smooth and finite, but has no boundary. This model avoids the singularity and the question of what came before. Time, in a sense, emerges gradually. It's a beautiful idea, mathematically elegant and consistent with some interpretations of quantum mechanics, but like others, it remains speculative. 7. Time as an emergent property. Another radical idea gaining traction is that time itself may not be fundamental. Some theories suggest that space and time are emergent, like temperature or pressure, which only makes sense when many atoms interact. In these models, the universe doesn't begin in time. Time arises only after a more fundamental quantum reality organizes itself. In such a picture, before the Big Bang may be meaningless, not because of a singularity, but because time didn't exist yet in any form we understand. This could explain why the laws of physics break down at the Big Bang. We're asking a question that doesn't apply. It's a philosophical as much as a scientific shift, forcing us to redefine what it means to ask when. Point 8. Is the question itself misguided? Physicist Sean Carroll has argued that we may be framing the question incorrectly. Instead of asking what came before the Big Bang, we should ask, why does our universe have the properties it does, including a low entropy, smooth beginning? The answer may lie not in a single moment, but in the overall structure of physical law or in the nature of reality itself. Perhaps we are one branch in a vast quantum tree, or one region in a timeless multiverse, or part of a deeper law we don't yet understand. What's clear is that the question opens more questions, and that may be its greatest gift. 9. Searching for clues in the present. Even if we can't directly observe before the Big Bang, we might find indirect clues. Certain patterns in the cosmic microwave background might contain traces of a prior universe, though current evidence is inconclusive. Primordial gravitational waves, if detected, could carry information from the earliest moments. Quantum experiments and advances in high-energy physics may eventually reveal hints of pre-Big Bang physics. We are still very early in this quest, but our tools are growing stronger. Conclusion: beyond the beginning. So what came before the Big Bang? We don't know, and perhaps never will, but this mystery is not a dead end. It's a frontier. Each proposed answer, whether it's bouncing universes, eternal inflation, or emergent time, reveals something profound about the limits of our knowledge and the boldness of our imagination. The Big Bang may not be the ultimate beginning. It may be a doorway to a deeper understanding, and the fact that we can ask such questions at all with mathematics, telescopes, and logic is one of the greatest triumphs of human thought. The Big Bang gave rise to everything we know: space, time, matter, and energy, but it may not be the whole story. In recent decades, physicists and cosmologists have explored theories that extend far beyond the traditional model, offering bold new visions of reality. Among the most provocative ideas are those involving the multiverse, string theory, and a range of modern cosmological models. These concepts attempt to explain not only the origins of our universe, but why it has the properties we observe. In this chapter, we venture into the frontier of theoretical physics, where speculation meets mathematics, and where the line between science and philosophy blurs. 1. The multiverse, one universe among many. Multiverse is not a single theory, but a family of ideas suggesting that our universe may be just one of many. This notion arises naturally from several lines of reasoning. Quantum mechanics, with its multiple possible outcomes, suggests many parallel realities, the many worlds. Interpretation. Inflationary cosmology implies that vast regions of space may form their own bubble universes, the eternal inflation model. String theory predicts many possible configurations of fundamental physics, leading to the idea of a landscape of universes. Let's explore these possibilities more closely. 2. Quantum multiverse. Many worlds from quantum decisions. In the 1950s, physicist whoever proposed the many worlds interpretation of quantum mechanics. Instead of a single outcome for each quantum event, every possible outcome actually occurs in a branching universe. Each time a particle could go left or right, reality splits. According to this interpretation, there are an infinite number of universes, each representing a different quantum history. In one, you're reading this chapter. In another, you never picked up the book. This view removes randomness from quantum mechanics, but at the cost of an exploding number of parallel realities. While fascinating, the quantum multiverse is difficult to test experimentally. Still, it has gained support among many theoretical physicists who find it logically consistent. 3. Cosmic multiverse, eternal inflation, and bubble universes. In the 1980s, the inflationary model of the early universe revolutionized cosmology. But, soon, it was discovered that inflation doesn't need to stop everywhere. In many versions of the theory, inflation is eternal, continuing in some regions while ending in others. The regions where inflation ends become bubble universes, each with their own version of physics. This process leads to a cosmic multiverse, where our universe is just one bubble among countless others. Each bubble might have different values, for fundamental constants contain different types of particles, even follow different laws of physics. Entire this diversity is known as the multiverse landscape, and it opens a fascinating possibility. We may live in a universe that permits life simply because it's one of the few that can. This leads directly to the controversial use of the anthropic principle. 4. Anthropic reasoning. Why our universe looks just right. Physicists have long puzzled over why our universe seems so finely tuned for life. If gravity were slightly stronger, stars would burn too quickly. If the nuclear force were weaker, atoms wouldn't hold together. There are dozens of such coincidences that seem essential for life. In a multiverse with billions or even infinite universes, it's no longer surprising that some would have the right conditions. The anthropic principle states that we should not be surprised to find ourselves in a universe suited for life, because only such universes can host observers. This principle is controversial. Some scientists see it as a philosophical escape hatch, avoiding deeper explanations. Others see it as the only reasonable response to the apparent fine-tuning. 5. String theory. A new foundation for relative multiverse becomes even more interesting when combined with string theory, one of the most ambitious attempts to unify physics. String theory proposes that all particles are actually tiny vibrating strings, whose vibration patterns determine their properties. But for the theory to work mathematically, it requires extra dimensions, usually 10 or 11. Beyond the familiar 3 of space and 1 of time, these extra dimensions are thought to be curled up at extremely small scales, forming complex geometries known as Calabi-Yau manifolds. Each different configuration of these dimensions corresponds to a different version of physics. This leads to an enormous number of possible universes, as many as 10,500, in what's called the string landscape. Our universe is one configuration among many. Again, the anthropic principle invoked to explain why we observe this particular one. 6. Brain worlds and higher dimension string theory also introduces the concept of brains, multi-dimensional objects that can span various dimensions. Our entire universe might be a three-dimensional brain floating in a higher dimensional space called the bulk. Other brains could exist parallel to ours, possibly interacting through gravity or exotic particles. In some models, collisions between brains create Big Bang-like events, a scenario called the ekpyrotic model. This offers a new twist on the origin of our universe, not a singularity, but a collision in a higher dimensional space. If true, the multiverse might not be abstract, it could literally be a stack of parallel brains, with physical connections between them. 7. Modern models of the multiverse, expanding the horizontally. Multiple research programs explore the multiverse idea from different angles. Cyclic universes. Some models suggest the universe undergoes infinite cycles of birth, death, and rebirth, possibly through bounces or brain collisions. Holographic universe, inspired by black hole physics. Some theorists propose that our 3D universe is a projection from a 2D surface, a hologram. This has radical implications for the nature of space and time. Causal set theory and emergent spacetime. Others suggest that spacetime itself is not fundamental, but emerges from deeper relationships between events, like a quantum network of cause and effect. These ideas are at the cutting edge of physics, beautiful, bold, and often speculative, but they all aim to answer the same fundamental questions. Why is the universe the way it is? Could it have been different? Are we alone in the cosmos, or in an infinite sea of realities? 8. Challenges and criticisms despite their elegance. Multiverse theories face serious challenges. Lack of testability. Many models lie beyond our ability to observe. If other universes don't interact with ours, can we ever detect them? Scientific versus philosophical. Some critics argue that if a theory can't be tested or falsified, it ceases to be science. Too much flexibility. With billions of possible universes, it becomes easy to explain anything, which risks losing predictive power. Even so, multiverse models arise naturally from well-established physics. We didn't invent them to be exotic. They're the logical consequences of theories like inflation and string theory. Some physicists propose indirect tests, for example, looking for collisions between bubble universes in the cosmic microwave background. Others hope that deeper understanding of quantum gravity may one day provide clearer answers. 9. Implications for philosophy and meaning beyond physics. The multiverse has profound implications for philosophy, meaning, and even identity. If there are infinite versions of you, living different lives in different universes, what does that mean for free will? For uniqueness? Does the existence of many worlds make our own less special or more precious? Some find the multiverse unsettling, others see it as a source of awe, a cosmic ocean of endless possibility. In either case, the multiverse challenges our deepest assumptions. It forces us to expand our imagination and to confront the limits of human knowledge. Conclusion: a universe among many. The Big Bang once seemed like the ultimate beginning, but modern theories suggest it may be just a local event in a much larger reality, a single firework in an eternal cosmic celebration. Whether through quantum choices, inflationary bubbles, string landscapes, or brain collisions, the idea of the multiverse invites us to rethink everything. We may never visit these other universes, but in studying their possibility, we learn more about our own. Perhaps the greatest lesson is this: the universe, or multiverse, is not only stranger than we imagine, it's stranger than we can imagine. For most of human history, we gazed up at the stars with all and no answers. We saw patterns in the sky, but we didn't know what they meant. We imagined gods, monsters, and myths. We invented stories to make sense of the darkness. But over time, curiosity transformed into science. We built telescopes to see farther, equations to think deeper, and theories to ask better questions. The universe began to reveal itself, slowly, imperfectly, but undeniably. We discovered that Earth is not the center, that the stars are suns, and that space is vast beyond comprehension. Then we found that everything, galaxies, atoms, time itself, emerged from a single moment, the Big Bang. It was a revelation. But it was not the end of the story. It was just the beginning. Each new discovery leads to more questions. What triggered the Big Bang? Why does the universe have the laws it does? Are we alone, or thus one reality among many? Today, we stand on the edge of knowledge. The Big Bang is no longer just a theory of beginnings. It's a gateway to the deepest mysteries of existence. Quantum mechanics, relativity, dark matter, multiverses, and strings. These are the frontiers of human thought. And yet, for all we've learned, the most humbling truth remains this: we still understand so little. But that's not a defeat. It's a gift. It means there is still so much left to explore, so much left to imagine, and so much left to discover. The story of the universe is also the story of us. We are not outside of it, watching from afar. We are born of stardust, forged in cosmic furnaces, and evolved to ask the very questions the universe allows. Perhaps one day we will know how everything began, and why. Or perhaps we won't. But the search itself is what makes us human, because the universe is not finished, and neither are we.